Functions. We're going to revisit the topic of functions. There's a good chance that most of the things that we're going to talk about you already know. However, take this as an opportunity to fine-tune your skills and possibly learn a few new things. The definition of a function. A function is a rule that assigns every element in D, which is going to be referred to as the domain, to a unique element in R, which is going to be known as the range. Okay, now that definition, there's something really particular in there, which says that every element in D is going to be assigned to a unique element in R. That means for every input that we put into the function, we get back one output. Okay, some things I've probably already mentioned here just as I was talking. The set D of all input values is the domain. Okay, D is for domain. These are your input values. We'll also refer to those as X's most of the time. The set R is going to be the range, and that's all the output values, which we usually go with the letter Y for that. Okay, so some other ways that we can refer to domain and range. We do have domain and range. The domain is the independent variable. It's also called the inputs, and we usually go with the variable X. The range will be the dependent variables, also called the outputs. We usually go with the variable Y, and when we start talking about this as a function, we tend to replace the Y with f of X. Okay, and that is read as f of X. Okay, the reason that we do that is because we have what are called relationships. There are sometimes relationships between X's and Y's, but that relationship won't be defined as a function. Okay, for every element in the domain, you don't get a unique element in R. You get different answers for inputs. Okay, so that would just be a relationship. But if it's a function, we might go with the notation f of X just to emphasize the fact that it is a function. The function notation is going to highlight the independent and dependent relationship between the variables. Okay, so the function notation tells us that our function called f is going to be dependent on whatever X you put into that function. And as a side note, you should already know this, but as a side note, this is not f times X. This is just a notation that says there's a function, some expression that we have that you would plug X into, and then it gives you an output, which on the coordinate system, if you're going to graph it, that output is usually going to get referred to as Y. All right, a relationship between two variables, an input and an output, can be viewed in a lot of different ways. One way that we can look at it is called a mapping. Okay, now a mapping isn't something that we tend to use. It just doesn't work out for a lot of functions. But if you do have a select set of ordered pairs, which is what we're going to have in these examples here, you can show them as a mapping pretty easily. The cool thing about a mapping is it does describe the definition of a function pretty good with examples of things that are functions and not functions. Okay, so what a mapping is going to do is it shows you the connection between an input and output. We have these ellipses, and what we do is assign the one on the left the input values and the one on the right as the output values. Here it could be X and f of X. Okay, if it is a function. If it is not a function, that really wouldn't make sense to use the f of X notation. Okay, but we'll work under the assumption that they might actually be functions. What we are going to do, though, is we're going to map these coordinates, and then we're going to decide if the mapping does show a function. And that's going to go back to the definition that every element in D has a unique element in R. Okay, so in the input bubble, what we're going to do is just list all of our X's that we have here. So we have a 0, we have a 3, a 4, and a 5. In the output bubble, we're going to list all of our Y values. We've got a 2, we've got a 4, you've got a 4 again, you don't need to write it twice. You also have a 6. Okay, so we have a 2, we have the 4, which is in both of those, you also have the 6. Okay, so the domain consists of 4 values. The range consists of 3 values. What the mapping is going to do is going to show how the inputs go to the outputs. So 0 as an input, if you put 0 into the function, it's going to give you back 2. Okay, if you put in a 3, you're going to get a 4. As well, if you put in a 4, you also get back a 4. If you put in a 5, you get a 6. So every element in the domain goes to some value in the range. The important thing is that every element in the domain has a unique value that it goes to in the range, which is what this shows us here. We do have the case that a 3 and a 4 both give you a 4. However, we can be confident that whatever this function is, that if you were to put a 3 in it, you do always get a 4 back as an answer. You just happen to also get a 4 as an answer if you plug in a 4. So this is a function. The second mapping, the inputs are going to be 1, 2, 3, and 1. Okay, so you got a repetitive 1, but you don't need to list that twice. So you've got 1, you've got a 2, and a 3. Okay, so the domain has 3 elements inside of it. The range, or the output, is going to have a 3, a 3, a 5, and a 5. So it only has 2 numbers here. It has a 3 and a 5. Okay, now a 1 as an input is going to give you a 3. 2 as an input also gives you a 3. And all that is all right for this to be a function. They just both happen to give you the same number. But a 1 gives you a 3 and a 2 gives you a 3. Okay, and then a 3 gives you a 5. But then here, at that spot, you get that 1 as an input gives you a 5. But previously, 1 gave you a 3. So there's a conflict right here. We have a conflict. That 1 as an input, something in D, does not have a unique value in the range. Sometimes it's a 3, sometimes it's a 5. The way that we want a function to work is that for every input, we want to know what the output will be. In this case, an input of a 1 could be a 3 or a 5. And therefore, this is not a function. Another way that we can look at a relationship is as a graph. This would make a little bit more sense if you didn't have a select set of coordinates, like what we did for example 1. Okay, so these graphs have an infinite number of points, even just within the window that we're looking at. Okay, as you move along that curve, there's an infinite number of points that exist. Okay, so you wouldn't build a mapping for this, but we still want to look at this with the same perspective of the definition. Do the inputs have more than one output? Does that happen? And if that happens, it fails to be a function. If it doesn't, if for every input you have a unique output, then this is a function. Okay, so what we kind of do is just move along the graph from left to right, and we check x values to see if you get more than one output. For example, at this x, you got one output, which is right there, and that's it. Okay, over here at this x, you get one output, which is on that spot. Skip ahead, you could go over here, you get one output, which is down there. But as you move along the graph, every x that you choose, you've got one output that's there. The same thing's true for the second picture. It's got a zigzag shape, which is kind of interesting, but for every x that you pick, there's going to be a select y value that goes with it. So over here it matches that, over here it matches there, right here matches down there. Okay, the third graph, some of it works, some of it doesn't. If you choose an x over here, you have one output, which is down there. If you choose an x over there, you got one output, which is up here. However, in the middle part of this, if we choose x to be -1, you've got an output here, you've got an output here, you also get an output down there. In fact, you get 3 outputs for the same input. So you could imagine in the mapping that we would have a -1 in that first bubble, then to the right, it would be pointing to 3 different answers. Okay, so this relationship here, because it's still a relationship between the x's and the y's, this relationship fails to be a function. So this is going to be yes, yes, this is going to be a no. That will not be a function. And the whole issue is right here in the middle. A way that we can physically test this is called the vertical line test. What we do is we take a vertical line and we move it from left to right along the graph, and we look to see if that vertical line crosses at multiple places. Okay, for example, right here. So I would take a vertical line, which would be the edge of the paper here, move it along. When I get to that spot, it crosses 3 times. Okay, over here, everything's good. You only cross it once. Cross it once. So these are all one output, one output. Right there, if you can see that, you actually get 2 outputs right on that little curve right there. And then as you move in this area, you have 3 outputs like what we had at -1. And you continue to have 3 outputs for every input up until you get to here, where you get 2 again, and then everything's good after that. So the vertical line test is a physical way that we can look at the graph to see if we're going to get more than one output for an input. Next, what we're going to do is talk about the domain and the range of functions. The domain of a function is the set of all possible input values, and we assume that the domain of the function is the domain of the algebraic expression. Okay, that means any x value that you can actually plug into the expression that represents our function. Unless the domain fits a situation. That would be if it's a word problem or some special case, you would have what would be referred to as a relevant domain. Okay, and that might not be the same thing as the implied domain. The third example that we're going to look at here, that is going to have a relevant domain because this is going to represent area. There's some context to the problem, which is going to take away from the original expression that we have. Okay, as we go through example 3, we're going to state the domain of each of these functions in interval notation. Interval notation is going to be using parentheses and brackets. In a way, it looks a little bit like a coordinate, but is actually different. Okay, our first function, f of x, is the square root of x plus 3. Okay, and as I go through the examples, I'm not going to work under the assumption that you know what these graphs look like. Instead, what I'm going to do is graph them for you. We're going to take a look at the graph and then discuss what the domain would be. All right, so for f of x, we've got the square root of x plus 3, which looks like that. Okay, that is half of a parabola on its side. It does have an endpoint at -3. Okay, we do have an endpoint here. The graph continues to go to the right. It continues to go that direction. And we can describe that it continues to go to the right because you can continue to plug in higher and higher x values. Okay, and what that means is I can choose a big number for x like 100. Plug in 100, I get 103. And 103, you can take a square root of it and you get a number, which means it's part of the domain. The 100 would be part of the domain. However, if I go to the left of -3, such as -4, if I were to plug in a -4, I get -4 plus 3, which is -1, and you can't take the square root of -1. You get an imaginary number. Okay, so values out here don't exist as part of the domain. What happens at -3? If you put -3 in, you get a 0, and that's okay. You can take the square root of 0. It just happens to be 0. Okay, so for this function, in interval notation, the domain has a lowest value at -3. It doesn't actually have a highest value, so we call it infinity. Okay, at -3, because -3 is part of the domain and not just a boundary, you can use a bracket, and we refer to that as being closed. Infinity, being that it just goes on forever and is not a well-defined endpoint, we use parentheses, and we say that it is open. For the next function, g of x, and yes, you can use different letters here. You just have one letter that you use for the function, so this is a function called g. Behind that, in parentheses, is going to be the input variable that you have. In this case, it is also x, so we read it as g of x. It is a function called g, dependent on x. Based on the numerator, we can probably already figure out that the domain is going to be limited, okay, because you can't have negative numbers in here. So we're looking at maybe 0 to infinity. However, you do have this expression in the denominator. You have x minus 5. The thing about a denominator is it can be anything but 0. You can't divide anything by 0. It becomes undefined. Okay, so we're thinking from the top that it could go from 0 to infinity, except there's one value here that you can't put in the function, which is going to be 5. Okay, at that one value, it just doesn't exist. All right, here's what the graph looks like. We'll take the square root of x, divide that by x minus 5. And that's the picture that we get. The function stops at 0. We don't have anything over here. Does not exist. In fact, I'll go to the table to show you. If you look at all the negative numbers, you get error. Okay, the graph does not exist to the left of 0. Does it exist at 0? Yes, it does. And it gives you 0. Okay, and then it continues to exist as you go to the right, except at 5. That one spot, that'll make this undefined. Doesn't exist there. Okay, so your domain's going to have two parts. It can be as low as 0, so that's a bracket, and it goes up to 5. It does not actually become 5, it disappears at that spot. So we're going to make it open. It then picks up immediately after 5 and continues to infinity. All right, for our third function, we have a relevant domain. This is A of S. That's the expression. A of S is going to be the area of an equilateral triangle with a side length of S. Okay, as an expression, if you just look at this, you have a number. I mean, it's got a square root in there and it looks complex, but it's just a number and it's being multiplied by S squared. So just as an expression, there isn't a value that you can't plug in here. You can square anything and it's fine. But because we're talking about area, which is dependent on the side length S, we have to think about what are relevant sides that we can have. Two things should come to mind. One, you can't have a negative side length. That doesn't make any sense. And two, you can't have a 0 side length. You have to have some positive number for the side length. So that means that the domain is going to be open at 0. It cannot include 0. And your side length can go to infinity.
Wait, what?